Okay, P chemists, continuing along, we're going to get into this construction of MO diagrams, and we're going to get into a lot more detail on these sigma bonds and pi bonds and how they are formed in homonuclear diatoms. So let's go for it, and you notice that I've got a little Mathematica simulation next to me, which will be the subject of our Math 9 activity. So, for constructing MO diagrams, a couple ground rules to lay first. So, electrons supplied by atoms accumulate in orbitals to achieve the lowest energy configuration subject to constraints by Pauli. Meaning, if two electrons have to occupy the same orbital, they've got to be spin paired. If several degenerate orbitals exist, then the electrons are added singly to each individual orbital before doubly occupying any one orbital. So added singly to each individual orbital before doubly occupying any one orbital. So that's just another way of stating the Pauli exclusion principle. And then once again, if two electrons do occupy different degenerate orbitals, then a lower energy is attained if their spins are parallel. So if we don't have to pair them up, if they can be in two separate but degenerate orbitals, the triplet state is the lowest energy configuration. Okay, so let's talk about these sigma bonds as we've discussed in detail. And so recall, sigma bonds are created from linear combinations of, in this case, I'm showing you s orbitals. And so to get this construction, we need to indicate a new term symbol, which is for symmetry. So we are going to use G to indicate even symmetry, G standing for Gerard, which is Z-Deutsche for even, or Ungerad, which is the Deutsche or German for odd. And we'll give that a U. So for example, if I look at the sigma orbital bonding state, where recall I had atom A and atom B, and I had enhanced constructive interference in the internuclear zone. That creates a bonding orbital where both orbitals now have the same phase, they're both positive. And if I take a center of inversion and draw a line across that center of inversion, if the sign doesn't change, then it has a Gerard symmetry, we give it a G. And if the sign does change, we give it an Ungerad, or a U, for odd symmetry. So we can begin to build up this orbital diagram with the following. We have our 1 sigma G, right, which is our bonding state, and our 1 sigma U, which is our anti-bonding state. And if you notice in this picture here, when we get these two 1s orbitals close to each other, it makes this kind of elongated looking shape. And we can play with that in the Mathematica here. So I've got two 1s orbital wave functions that I can manipulate to get closer and closer. And you can see when I get them to a certain spot, I have this enhanced electron density in the internuclear zone corresponding to a bond. I can also look at the anti-bonding state, and if I go back now to two separated 1s orbitals and I try to bring them close to each other, you notice that they have this effect of like repelling each other, right? And so the closer and closer I get them, the more they're repelling each other away. So we have a node in that internuclear zone. Additionally, the appearance of these energies are based on our energy solutions that we discussed. So we think of the top of this diagram related to some threshold describing ionization. So the energy of H1s is given to us by the Rydberg constant, right? So that was our solution for hydrogen 1s. The 1 sigma G is given to us from our bound state, right? Recall that that had this shape that looked like this, where now the minima of that corresponds to 1 sigma G. And then the 1 sigma U, the E minus, right? So recall that was from E plus. And then the E minus solution had this repulsive state, right? And so now the difference between those is represented in our graph by this difference right here, which is pretty cool. So each hydrogen brings one electron to the party. We bring them down and pair them up to make a 1 sigma G bond. Beautiful. So what happens now if we try to move up one position in the periodic table? So again, we have one electron from each hydrogen. They come together first into the lowest possible orbital and make this singlet state. Well, recall helium can bring 2 electrons to the party each, so that will be 4 electrons in total. So as we bring them in here, you can see we create a sigma state in the bonding orbital, or excuse me, we create a singlet state in the sigma bonding orbital, and we create a singlet state in the sigma anti-bonding orbital. And so what this means is helium cannot exist because it's helium-2, I should say. Helium-2 does not exist because the number of bonding electrons it has matches the number of anti-bonding electrons. So this is where we came up with that equation you used in general chemistry called bonding order, not body odor, but bonding order, which equals 1/2 the number of bonding electrons minus the number of anti-bonding electrons. And so for helium-2, right, we would have 2 minus 2 equals 0, so there is no bond there. For hydrogen, we would have 2 minus 0 times 1/2. So my bonding order in H2, I wrote 0, but I wanted to say 1. So the bond order of H2 is 1, and hopefully we remember that from our Gen Chem days. It just has a single bond. Okay, let's move on to the more complicated bonding schemes. So as noted, we can make a sigma bond out of 1s for H2 and H2 only, right? So we'll say H2 is a 1s plus 1s situation to make 1 sigma Gu. And I'll say 1s plus or minus 1s to make either 1 sigma G or 1 sigma U. With everything else, it's going to be some linear combination of 2s and 2pz, and specifically 2pz, because remember, we're defining the internuclear axis as the z-axis. So then the other dimensions are x and y on that scale. So now, noting that once we're past H2 and really past helium-2, right, we have to use 2s and 2p. So our complete basis set becomes the following. We can have linear combinations of 2s, linear combinations of 2s, right? We could have these linear combinations, and we could have these linear combinations. So generally, our linear combinations of 2s or even 1s, we call the 1 sigma G 1 sigma U. Linear combinations of 2pz to make sigma orbitals, we call 2 sigma G or 2 sigma U, because it still is making a sigma bond. And we can, I've got a picture of it right there, but we can see it in my static model with the following. So I've got 2 pz orbitals now oriented towards each other, right? And as I bring these closer together, lo and behold, they make this lovely cylindrical symmetry in the z-axis. And we also have these orbitals that are appearing outside of that range, which are places in which lone pairs could exist. And now if we think about our symmetry operation here, and I'm going to draw this line noting the z-axis, you can see with our G, our bonding orbital, it is such because if I draw an arrow over the center of inversion, the sign doesn't change. But now if I do that with the anti-bonding orbital, the sign does change. So this was from positive combinations, constructive interference. This was from negative contributions or destructive interference. And so now it's also important to note that as we get into atoms in which they contain both 2s and 2pz electrons, we can actually get further mixing known as S and P mixing, which is going to change the energy of our sigma orbital depending on whether it came from combinations of 2s, 2pz, or combinations of both 2s and 2pz. So that's what that S and P mixing is referring to. So, but before we get into that, let's talk about pi bonds. So I'm going to scroll up here on my manipulate, and we'll get into that. So when we make linear combinations of 2pz, as noted, it makes a sigma bond. Well, if we make linear combinations of 2px or 2py, we make pi bonds, very similar to what we talked about in valence bond theory. So, for example, if I've got two 2px orbitals oriented in this way, and I bring them close together, as we can see here in my Mathematica simulation, I make these lovely pi orbitals, which are above and below the internuclear zone, right? And of course, on this Mathematica simulation I've got here, it's just a two-dimensional representation. I don't have a way of pitching that in and out of the screen. So as we imagine, the 2py would do a very similar thing as the 2px, just rotated 90 degrees. So now, what about when we make destructive interference between those? Well, just like in the case of the sigma bond, we'll have this node in the internuclear zone, right? No constructive interference occurs to make that anti-bond. So now, when we consider our symmetry operation, the opposite happens as did in the sigma bonds, okay? So for example, to get my two p orbitals to combine constructively, the two phases have to be oriented correctly. So the positive lobe has to be oriented with the positive lobe, and the negative lobe has to be oriented with the negative lobe. Well, as a result, that's going to end up with an Ungerad symmetry operation for bonding, right? And for anti-bonding, now the two signs are flipped, which is what gives us the destructive interference. So that actually gives us the Gerard symmetry for the anti-bonding. So that's important to note, that that symmetry operation is the opposite in pi bonds as it is in sigma bonds. Okay, so let's keep going with this. I know this is going to be a little bit of a long one, but hopefully it's also somewhat familiar from your Gen Chem days. So now, building these up, we end up with a situation for diatoms, for homonuclear diatoms, when the p block is less than half filled and when the p block is more than half filled. And those differences come from this S and P mixing. So as we're building this up, we might recognize that 2s comes before 2p, right? Recall, these are AOs over on this side and MOs in the middle. So linear combinations of 2s gives us the 1 sigma g or the 1 sigma u. As it turns out in calculations for simple homonuclear diatoms that are less than half filled in the p block, the pi orbitals are lower in energy. So our pi xu and our pi yu are lower in energy than our 2 sigma g. So recall, these come from px and py. The 2 sigma g comes from pz, and then, which is why we end up with 3 of them, right, for our 3 p positions, okay? And then now we get our anti-bonding. So remember, the g, pi g is anti-bonding, and sigma u is anti-bonding. So now when we have things that are more than half filled in the p block, you notice here the order of the pi and sigma bonds switches. And that's predominantly due to energy lowering of the sigma bond. So the sigma bond lowers in energy greatly. And I'll show you a figure of that here in a moment. So now I'm using oxygen as a good example for occupying this diagram. So we recognize our electron configuration for atomic oxygen would be 2s2, 2p4. So I've got 2 electrons in each 2s, and I've got 1, 2, 3, 4 electrons in each 2p. And so that means I'm going to have 1, 2, 3, 4, 5, 6 times 2. I'm going to have 12 electrons occupying this diagram. So let's do that. Let's bring them down. So the 4 electrons I have in the 2s level completely occupy the 1 sigma g and 1 sigma u. And now as I bring these down, I first have to pair up the 2 sigma g. Then I can add 4 electrons to the pi u. And finally, I've got 2 electrons left over, and I'm not going to pair them up. Remember, the triplet state is lowest in energy. So those will appear as spin parallel, giving us the lower energy state. And now, as a result, we can write the O2 molecular electron configuration as the following. 1 sigma G2, 1 sigma U2, 2 sigma G2, 1 pi U4, and 1 pi G2 would be our molecular electron configuration. And we could have even specified if we wanted to. Like, for example, I wrote 1 pi U4. So we could have wrote that as 1 pi XU2 and 1 pi YU2. We could have actually broken those up into the 2 X's and Y's. And when we go to do molecular term symbols, we'll see that that's important to recognize, that those 4 electrons are really distributed over the pi X and pi Y. Okay, so let's take a closer look at this S and P mixing, and this will be the last slide of the video. So these are from calculations. These aren't just like made up. So calculations. And so what you'll notice here, particularly with the 2 sigma G orbital, it massively lowers as we go across the periodic table. And notably, what we'll see here with lithium-2 and beryllium-2, they don't have p orbitals available to them, right? Both lithium and beryllium only exist in the 2s subshell. But now once we get into boron and then onto carbon, nitrogen, oxygen, and fluorine, those have 2p electrons available. And so our 2 sigma bond is going to have mixing from both the 2s level and the 2pz level. And the result of that is it massively lowers the 2 sigma g orbital, particularly once we have a half-filled subshell, or more than a half-filled subshell. And that's because we've completely occupied the 2 sigma g and the 1 pi u. And of course, notably, the 1 pi u energy is going down just very slightly, but it's really this massive decrease in the 2 sigma g orbital resulting from all 4 of those combinations, 2s and 2pz, combining to make a 2 sigma g orbital. Okay, folks, that is it. In the next video, we're going to get into the hideous details on how to construct a heteronuclear MO diagram. And with that, we're also going to talk a little bit about some molecular modeling and computation. Okay, I'll see you in the next one.